Okay, so now what we are going to do is look at a very classical and well commonly used sorting algorithm called merge sort that uses a divide and conquer strategy. So what we will do is given say an array of and it's a sorting algorithm like insertion sort and bubble sort. So given a sorting algorithm, given an array, how merge sort will run is it will divide that array into two subarrays of equal length, and then it will use again the merge sort procedure of recursively sorting all the subarrays. So after we go through the recursions here, which I'll explain soon, you would have sorted this subarray, right? So 8329 will be sorted to 2389. Similarly, the 7154 will be sorted to its subarray, which is 1457. So now we have to merge the solutions of the two subarrays, of the two sorted subarrays, to get the larger subarray, to get the larger array, sorted array. Okay. So how do we merge the two sorted subarrays is what we are going to see. So let me explain the logic with this example and then look at the pseudo code and go back to this example again. So assume that we have this array here. It is divided into two subarrays. We go through a sorting procedure to sort the subarray alone and make it like 2389, and same thing here, 1457. So how do we merge two sorted subarrays? That's what we're going to see. So what we'll do is we'll start with a pointer or index to refer to what element we are currently looking at. So I'll call this just as an index I, and in this sorted array and j here. So what we are doing here is so we are given the input array, and we want to, when you divide this, we are dividing into two subarrays and storing it in some new arrays. So we are dividing into two subarrays. If given A is a larger array, you are dividing to two subarrays B and C, and basically sorting B and sorting C. So we are going to merge the solutions of sorted B and C and overwrite to the input array A. Okay, so you have to remember that. So we will start with some index. So the pseudocode I use I and j. So I is pointing to the first element in the sorted subarray, left subarray, and then the sorted right subarray we have j. So we'll compare the values at index I and j each time, and whichever index has the smallest of the two values, it will write that index to our input array. So let us call this as k. So in this case, the element at index j is smaller, so 1 is returned to this position, which is 1 is going to override this 8. Okay, it's going to be 1, and since 1 is returned here, k moves to the next one, and we wrote 1 from j, so j also moves to the next element. So now comparing 2 with 4. So 2 is smaller, so write down the 2 and move our k to the next element. So k is 3. Alright, so that means I has to be now moved because I is no longer at 2. 2 has been written there. So now compare the latest value of elements at index I and j. So 3 and 4, 3 is smaller. So write down 3 as part of the output array and then move k. So since 3 comes from this subarray, I is now moved to 8. Now we have to compare 8 and 4. 4 is smaller, so we write 4 to the merging array. And move the pointer for j. So j is currently at 5. So I is 8, j is 5. 5 is the smaller of the two. So we write down that as the next cell, 5. Then compare move j, which is now at 7. Compare 8 with 7. 7 is also smaller, so write down 7 here. So we're basically done with the second subarray. We are still at index I pointing to 8, and then we have 9. So since that's a sorted portion, you can write down the entire sorted portion starting from index I. We are done with j, so we can write the rest of the remaining sorting portion. So it's 8 and 9. So this becomes 8 and 9. So that's how you merge two sorted subarrays into one larger array. Okay, so let's look at the pseudo code and come back to the example, and that will reinforce what we just went through. So if you want to do merge sort on an array of size n, index from 0 to n minus 1, you first check if the problem size n is greater than 1, because if your n is 1, then your array has only one element which is by itself sorted, so you don't need to run merge sort. So if n is greater than 1, basically copy the first half of the array A to a new array B, and the second half of array A to a new array C. So basically, if you look at it from index 0 to n over 2 minus 1, so the array has, in this example, 8 elements. 8 over 2 is 4. 4 minus 1, which is 3. So the elements at index 0, 1, 2 and 3, which are 8, 3, 2 and 9, are copied to this new array B, and their indexing starts from 0 to n over 2 minus 1. So n is 8, 8 over 2 is 4, 4 minus 1 is 3. So the index for B is 0, 1, 2 and 3. Now copy the second half of A starting from index n over 2 to n minus 1. So n is 8 in this example, so 8 over 2 is 4. So you see everywhere I use a floor symbol to take care of the divisions where the n is an odd number. So if n is say 9, 9 over 2 will be 4. So in that case 4 minus 1 is 3. We'll copy elements 0, 1, 2, 3 to B, and n over 2 floor. So 9 over 2 floor is 4, and starting from 4 to 8 will be copied to C. Okay, so the index for C will be 0 to n over 2 with an upper bound up minus 1. So why is that? Again, if n is 9, you're going to have one more element in C compared to B, because you see B will have 9 over 2 minus 1, which is 4 minus 1, which is 3. So B is going to have 0, 1, 2 and 3, 4 elements. Totally there are 9 elements. So C is going to have one more element. So that's why we wrote it as a seal symbol. So yeah, seal symbol, n over 2 minus 1. So in case of n to be 9, 9 over 2 is 4.54. That is if you're flooring, but here we have n over 2 4.5, but a seal, so it is 5 minus 1. so 4. So the index for C will be 0, 1, 2, 3 and 4. So that is 5 elements. Okay, so I'm explaining the very minor details of the indexing. So in this case, so you see what happens, you are copying the contents of A to some new blocks of memory B and C. The total size of B and C combined will be n, because you are having the first half in B and second half in C. But you see, this is an additional memory usage. Unless like insertion sort and bubble sort and the other algorithms we saw in 228, selection sort, heap sort and all those stuffs, they do not use additional memory that grows with input size. Okay, so all those stuffs will use just a constant temporary variable. For any array size, we just use 2 or 3 temporary variables. It doesn't grow with input size. Whereas merge sort goes to this strategy of dividing the or copying the first sub half of the array, input array, to a new block, and the second half of the array to another new block. So you use 2 sub arrays. The total size adds up to the length of the array A. So if your array A has 1 million elements, you need to create another 1 million elements in memory. In addition to storing the input array A, you need to create another block of memory, or 2 blocks of memory actually. The total size of which will be n elements. So merge sort will have a theta of n space complexity. It requires additional space proportional to theta of n. So you always remember that. So then what we do, the pseudocode, you see, I call merge sort on B. So if you look at this, I'm calling merge sort on B. So I'm going to divide this to B and C, and so this is more easy to look at. So I'm running now merge sort on B. So that's what I have here. So merge sort of B is this function, so it's recursive. So calling now merge sort on B. So I'm going to go ahead and divide this B into 2 subarrays. So for this new instance of merge sort that we call, that's actually the B subarray is now treated as A subarray for that instance of merge sort. So this is treated as A subarray, and you're dividing that to B and C, the 2 subarrays. And then after you divide that into 2 subarrays, 8, 3 and 2, 9, you are again calling merge sort of B. So you see, I indicate the sequence of recursions. So this is the first recursion. You're dividing A to B and C and calling merge sort on B. And then you are dividing this into B and C and calling merge sort on this one. It's the second recursive call. Then once you have these 2 smaller subarrays B and C, you are again calling merge sort on B. That means you are again splitting this into 2 subarrays of length 1. 8 is one subarray, 3 is another subarray. Now you see here, we do all these things if the array size that you want to sort is greater than 1. So at this point, when I call merge sort on B and control goes back to the larger one and this becomes our A, this array is of size 1. So we really don't need to do anything. So we do all these things only if n greater than 1. An array of 1 element is sorted by itself. So we just leave it as it is. And the control goes back to the next statement in the recursive call. So you called merge sort of B when you divided this array into 2 subarrays. So this is our B and this is our C. So you are now going to sort C, merge sort C of size 1. Again, it is already sorted, so you're not going to do anything, and control comes back to the calling function, which is this, and you are going to merge the 2 sorted subarrays and overwrite the A. So this is our A that was split into B and C, and B and C have been now sorted, and you're going to overwrite or merge the 2 sorted subarrays and overwrite the A. So now we need to look at the code for merging two sorted subarrays B, C, which are the two sorted subarrays, into the larger array A. So for that we'll use this I and j, this thing to understand the pseudo code, and then we'll come back to the sequence of recursion calls. Okay, so let's look at the pseudo code here. So we're going to merge B and C. So let us say the index for B runs from 0 to P minus 1, C runs from 0 to Q minus 1, and A will then go from 0 to P plus Q minus 1, because we're going to merge these two arrays into A. So use I, J, K as the index for B, C, and the merging array A. So let us do that. So initially everything is in the first index. So I equals 0 pointing to this index, and J is also 0 pointing to this index. So we run this loop while I less than P, J less than Q. So P is the length of this subarray, Q is the length of this subarray. So that's why the indexing goes from 0 to P minus 1, and here 0 to Q minus 1. So I should be less than P, J should be less than Q, okay, the length of the two subarrays. So if B of I is less than or equal to C of J, so basically like here, B of I is 2, C of J is 1. 2 less than or equal to 1, it's not the case. So 2 is greater than 1. So we'll go to the else part in this example and write into A of K C of J. So that's why we wrote C of J 1 to A of K. And then once we do that, we need to increment the J by 1. So J is now pointing to the next index, and K is also incremented because we are ready to write at this new index of K, which is 1. So we say J equals J plus 1, and after if else we increment K, because either from B or C we are writing into A, and we need to increment K. So now I is still at index value 2, J is now pointing to value 4. Now compare B of I with C of J, 2 is less than 4. So now we get to write B of I to A of K. So 2 is written to A of K, and what we increment is I equals I plus 1. So I is now moved to the next index. So we keep doing that. We compare B of I with C of J, and whichever is the smaller of the two, we write that and move that index I or J accordingly to the next value. So and then K also, of course, with respect of either B or C, after you write into A, we increment K. So we keep doing this until we reach the end of the subarray for one of them, at least one of them. So once in this example, we wrote what things from J were written to A. So we wrote 1, 4, 5, and 7. So when 1, 4, 5, 7 were written, I was pointing here, right? So we had 8 compared with 7. 7 is smaller, so 7 was written here, and I is still here, but J cannot be any more incremented. Already J has become Q minus 1, 0 to Q minus 1 are the valid values of J. Now when you do J equals J plus 1, J becomes Q, and the loop runs well I less than P and J less than Q. So J is now Q, so you cannot run this loop anymore, so you have to come out of the loop. So when you come out of the loop, check which of the two subarrays have been completely exhausted. So in our case, the J subarray was completely exhausted. So we check if I equals P. In our case, no, I is still not P. I is 0, 1, 2. P is what? 4. That's the length of the subarray. So I is not P. So we go to the else part. So the else means we have J being equal to Q. So when you come out of the loop, either because I became equal to P or J become equal to Q, that's why you come out of the loop. So that's what you're going to check. If I equals P, or j equals q. So in our case, else j equals q. So in that case, we copy the rest of the b subarray to A. So the b subarray is still now from I. We have to copy up to p minus 1. So that's why I say copy the b subarray from I to p minus 1 to k, where so to A. A is still like we are done at k, right? So we have to move k equals k plus 1, isn't it? So k, this is the next index we can write into. So we will write these elements from I to p minus 1 to k to p plus q minus 1. So p plus q minus 1 is the last index of A. Okay, so in this case 4 plus 4 minus 1, 7. So p plus q minus 1 is 7. That's the last index of A. So that is if the C array was completely returned to A and we are running the remaining portion of B. If I equals P was the reason we came out of the loop, then we have to copy the remaining contents of C, which will be similarly from J to Q minus 1, starting from J, whatever the value we have to write up to the end of that C subarray, to A of K plus K to P plus Q minus 1. So this way, once one subarray is completely returned to A, the other subarray, starting from whatever the element we have to write, we just write that rest of the array to A, because this portion is sorted and we're just writing that, adding that or appending that to the end of the array where we were merging. Okay. Any question on the merging process before we go through the recursion again? Alright, so we are out of time now, but what I want you to go through is, now that I went over this merging part, so next time we will come back and go through the sequence in which we are calling recursion. So basically you have to understand that we go all the way down, it's like deep as possible. So in order to sort this subarray, we are dividing into two subarrays, and then you call merge sort on this subarray, and then call merge sort on the left half first, and then once you merge the two sorted subarrays, you call merge sort on the right subarray and get the right subarray sorted. Then merge these two to get this left subarray sorted, and only after you get this left subarray sorted, only after you get 8329 sorted as 2389, you are calling merge sort on 7154, dividing that into two subarrays and then merging them, and then merging these two subarrays to get this one. So the numbers I indicated will show you the sequence of recursive calls. And always remember, if you want to merge to sorted or get a merged sorted array, like if you want to get 2389, the two subarrays should be sorted. So this subarray should be sorted, 83 should be sorted, and 29 should be sorted. So only if you get both of these sorted, we can get this merged subarray. Similarly, to get this one, you have to get 71 and 54 sorted. Like that, if you want to get the entire array sorted, you want to get these two subarrays 8329 as well as 7154 sorted. Okay, so go through this, and we'll come back and go through a little more detail of these numbers, in what order we are calling the recursion, and then we'll do the time complexity and move on. Right. So your first assignment is due next Tuesday.